Welcome to the strategic learning session. Today, we'll be talking about consistency of empirical CDF. This presentation explores pointwise versus uniform convergence in function sequence. We'll use examples to illustrate these concepts and discuss the Glevenko-Cantelli theorem and its implications. Let's dive into the world of statistics. Condition for non-application. To understand why the first condition mentioned here, the first condition is the first condition is not same as a second condition. The first condition is not same as a second condition. Let's find a specific condition where this holds true. That is, where first condition is not equal to second condition. Where second condition is the Glevenko-Cantelli theorem. Pointwise convergence. Given fnt converges to ft for all t, meaning for each t, as point approaches infinity, as infinity, ft will converge to ft. So here's the example of that. For any given t, as n approaches infinity, t by n approaches 0. Therefore, ft converges to ft. Supremum analysis. Now, let's think about another example where we subtract fn minus ft, where fn is a sample CDF, where ft is a true CDF, and we'll take supremum over t. Supremum is equal to infinity, especially when t is equal to n, indicating it never goes to 0. Because fn can goes to infinity, then t also can go to infinity. So it is never equal to 0. What's the scenario? If you are allowed to take the first worst possible t, which may depend on n, then what we can say is that for t equal to n, this is the worst case, and n is infinity, then fnt minus ft is equal to 1. Say if n is not infinity here, but it is a very large number, then still t, if is equal to n, then ft minus ft is still 1. This doesn't approaches 0. What I mean is that, what I mean here is that, now, what do I mean by that? Now let's write it down. Here t, ft equal to 1. So what we're saying is that even though we'll take the t, and it is not infinity but a little bit less than that, and it is equal to n, where n may be infinity, first possible worst possible case where t is equal to n, then still this condition holds true. This condition holds true. This doesn't approach 0 as n approaches infinity, even replacing t with a minimum of, even if you replace t with minimum of tn. Its difference remains fnt is equal to ft equal to 1, indicating it never goes to 0. Example of convergence. Now, pointwise convergence. For a given point t, fnt converges but not uniformly. Uniform convergence fails. The failure occurs when order of taking limit in t and n changes. If t, fixed t, let n approach let n approach infinity, it is a pointwise convergence. Pick the worst case t depending upon n. Supremum never goes to 0. These are two example of the where the uniform convergence fails. Livingko-Cantelli theorem. This theorem ensures that this pathological scenario of non-uniform convergence does not occur. Being aware of such pathological cases is essential even if they seem immediately irrelevant. Compact set analysis. Supremum problems arise when T takes values in an unbounded set. If T were in compact set, convergence issues would be mitigated. If T takes an infinite number of values, allowing to be for better control. In summary, the forward convergence happens at individual points, while uniform convergence requires uniform behavior across all points. We saw examples where forward convergence did not imply uniform convergence, highlighting the importance of limit order. Levinko-Cantor theorem helps us understand when uniform convergence is guaranteed, demonstrate the need to differentiate these type of convergence in function analysis. That's all for today. I will see you next learning session. Thank you so much.